Hello and welcome. So in this video we're going to be talking about returns to scale. This video is kind of designed for an intermediate macroeconomics course, so where returns to scale comes into play in microeconomics as well, with utility and firm production functions there. I plan to cover returns to scale relevant to an early course in macroeconomics, so production function for like an entire economy. In this video we're going to just kind of overview what we're going to do. I'll discuss the production function and exactly what we mean by returns and scale and returns to scale. Then we'll talk about the three types of returns to scale, increasing, decreasing, and constant. And hopefully at that point you understand the difference between the three. And then I'll show you how, given a production function, you can calculate what type of returns to scale that production function is, which is, just so you know, a fairly typical question you'll get early on in an intro or intermediate macro course. And then at the end, you could skip over those parts. I'll just kind of have a short cheat sheet of the three types of returns to scale and how you find it and what it is. And then also talk about like the distinction between returns to scale and diminishing marginal returns, which is sometimes confusing for students early on. Okay, so let's get started with production function and what we mean by returns and scale. So here are four different production function examples. Here's one production function, here's another, and another. Something you're given on an exam or a problem set might take any one of these forms. A production function, as a reminder, is a function that specifies the output of a firm or an industry or an entire economy. And since we're dealing with macroeconomics, think of this production function as that of an entire economy for all combinations of inputs. So this production function takes these inputs. So we got K and L here. They're called factors. So we have capital and labor, but you could also imagine energy and land and other things. But in early courses of macroeconomics, we usually just keep it down to two factors, capital and labor. And then the production function tells you how much the economy, so many firms, converts these inputs into some quantity of output. So for these factors, think of them as a number. So like capital is 3 and labor is 5. And you can think of it as a number being, so how much money is being spent on that factor, or maybe like how much money is being spent on that factor. For output, right here, it's also sometimes referred to as production or quantity or real incomes or gross domestic product. Think of output as a number, or think of it as like a number that reflects like the value of that production. So, for production in these examples, I've listed here Y for output. I've also listed Q. I've also listed P for production. These are all like just notations that I've seen in macro courses and micro courses. So don't be confused. They all refer to the same thing. Notation varies only because, economists haven't perfectly settled on a perfectly consistent notation. And then the professor that you have or teacher that you have will usually write what they've learned or copy off the textbook that they've been using. So I've learned from MainQ and a textbook written by Jones. And most macro textbooks are going to use this Y reflecting output or production, but don't be confused. You sometimes see Q and P in other textbooks, especially in microeconomics. Okay, so starting with production function, we can now talk about returns to scale. So returns to scale refers to how much output that Y changes given a proportional change in all the inputs, where all the inputs change by the same factor. So let me just write that down 1 second. So returns is that's how much output changes. And then scale refers to given a proportional change in all of the factors. Okay, so now usually students are kind of staring at me blankly, and I realize I should probably find a better way to explain this, but returns to scale is pretty simple. Suppose you double your inputs. So we're starting off with this top production function here, where output is equal to this kind of modified, or this Cobb-Douglas production function, and then we're going to double the inputs. So we now have twice as much capital and twice as much labor, and then the capital gets fed into there, twice as much labor gets fed into there. So given that we've, increased the inputs by the same proportional amount, that is to say in this this example, we've doubled capital, we've doubled labor. Now the question is, how much has output increased? Is this new, the level of output given this doubling of the inputs, is that the same? Is that exactly twice as much as the initial production, or is it less than twice as much, or is it more than twice as much? So if we, for example, double the inputs and we exactly double the output, we refer that to constant returns to scale. If we double the inputs, but that's less than twice the initial output, then we refer that to as diminishing returns to scale. And then if we double the inputs, but we get more than double the output, we refer that to increasing returns to scale. So let's do a couple examples, in fact, all 4 of these examples, and discuss what happens. So starting off with this production function. So this is like a kind of a parameterized Cobb-Douglas production function here, where output is equal to k raised to the 1/2 times L raised to the 1/2. So is this increasing, decreasing, or constant returns to scale? So to find out, what we're going to do is plug in, we're going to add in a scaling factor. So let me show you how you do that. I'm just going to put in a z in front of it. So a scaling factor refers to the amount by which we are changing the factor inputs. So sometimes, I've seen it in classes as omega, where we increase everything by omega. All that's just notation. In the kind of example I went over just a second ago, we just doubled the inputs. Whatever it is, it's a scaling factor, and it's how much we're increasing those inputs. And we're putting that scaling factor in front of all the inputs. So there's capital and labor, so we put the scaling factor in front of each. So now we have to add that z in front of all of the factors inside the production function. So we plugged in the z here. So now we're going to try to simplify this expression here. We're going to pull out the z's to the front. So we're going to pull out our scaling factor to the front. So the one with k has a k to the 1/2. So I'm going to pull out the z to the 1/2. And then the one next to labor has a z raised to the 1/2. So I'm going to have to pull out a z raised to the 1/2. Sorry, z raised to the 1.5. Sweet. So z to the 1/2 times z to the 1.5, what's that equal to? That's going to be equal to, that's equal to z squared. And then we still have k and L just as it was before. So now we have z squared times the initial level of output, right? So you could think of as this being some initial level of output, so y sub naught. You could think of it as this some new level of output, so y sub 1. Just cleaning up stuff. So how has output changed? Where this is just equal to y naught. So you can see our new level of output, y sub 1, is equal to our old level output, y sub naught, times z squared. So is this increasing returns to scale, decreasing returns to scale, or what? Well, z squared, anything greater than 1 squared is going to be greater than 1. So we know that z squared is going to be greater, z squared times the initial output is definitely going to be greater than what we started off with. So in this case, we have increasing returns to scale. Because we've increased the inputs by some amount, this scaling factor z, and we found that output was something more than just twice the initial output. We increased the inputs by z, but what we found is when we plugged that into the production function, it's now more than z times that initial output. So we have increasing returns to scale. So let's do a couple more examples. So let's start off with this production function here. This is a Cobb-Douglas production function that's been parameterized already. So yeah, let's add in the scaling factor. We have an initial output equal to this level, and now we're going to have our new output where we scale it by that scaling factor z. So in order to add that in, we got to put in the z in front of all the factors. So now let's pull out z in front of everything. So you got a z to the 0.3 from capital, and then you have a z raised to the 0.2 from labor. So remove those out. So z raised to the 0.3 times z raised to the 0.2 is just z to the 1/2. And then these guys are just what that initial output was here. So you know that this k to the 1 to the 0.3 times L to the 0.2, that's exactly what our initial output was equal to. So we could just plug in that. So our new output, given our, we increased all the inputs by this like constant proportional change, the scaling factor, we've increased the output by z raised to the 1/2 times the initial level of output. So is that greater than just z times the initial level? Or is it equal to? Or is it greater than? Well, this is less than. So it's z raised to the 1/2, so this is square root of z. So for any value of z, 1 or more, if you raise that to the 1/2, that is to say if you take the square root of it, it's going to be less than that initial value of z. So given an increase of z, you're going to have, so output has increased by less than that little proportional change we've increased the inputs by. So this is diminishing returns to scale, decreasing returns to scale. So let's do another example that's kind of a different type of production function that we haven't seen before. So if initial production function is this 3k plus 2l, so let's do the scaling factor we always do. So the new level output is equal to twice the initial, or sorry, z times the initial input. So we also have to double our inputs in here. Sorry, increase by z the inputs in here. So we have 2 times z times L. Okay. So we could pull out z from both of them, from in front of k here. We could also pull it out from in front of L. And so we have z times that initial level of output. So you can see in this step, all I did was take out the z here and the z here, and we now have something equivalent, which is z times 3k plus 2l. And remember what 3k plus 2l is equal to. 3k plus 2l is exactly equal to our initial level of output, so y sub naught and then y sub naught is obviously equal to z times y sub naught. So here we have constant returns of scale. Sweet. Okay, one last example. We'll do just a Cobb-Douglas production function here. So this form of the production function is a Cobb-Douglas. So you have A, which is like technology. You have K for capital raised to the alpha, and then L for labor raised to the 1 minus alpha. What do you think this is going to be? You actually, if you're familiar with Cobb-Douglas production function and you see these exponents, you actually should be able to tell what kind of returns of scale it is pretty quickly. But let me go through the math to show you what it is. So we've increased the inputs, capital and labor, by z, and you can see I've distributed z throughout there. So let's add that in. So I'm going to pull out z from capital, So it's going to be z raised to the alpha. Oh, I misspelled alpha. Sorry. And then I'm going to pull out the z in front of L. So that's times z raised to the 1 minus alpha. And then we have k. So we have a times k to the alpha times L to the 1 minus alpha. That's just initial output. So I can put a little y sub naught there. And then what's z to the alpha times z to the 1 minus alpha? Well, you know we just add the exponents together. So you have z to the alpha. So that's going to be alpha plus 1 minus alpha. And then alpha plus 1 minus alpha is just 1. Just simple arithmetic there. And then z to the 1 is just equal to z. So with a Cobb-Douglas production function, and this was kind of like a generalized Cobb-Douglas production function, where you have one factor raised to the alpha, the other factor raised to 1 minus whatever the other one was. So this is going to be constant returns to scale. And in fact, this kind of particular way we have a Cobb-Douglas production function, which you'll see in most macro courses, sometimes it's alpha, sometimes a beta instead of an alpha, but it's raised, something's raised to some Greek letter, and the other factor is raised to 1 minus that Greek letter. That's going to be a constant returns to scale. And Cobb-Douglas production functions, most of the times you'll see have constant returns to scale. So we have a couple examples here. We have one with an increasing returns to scale. Increasing returns to scale you usually see with like a single firm, where a single firm, there's opportunities just to reduce average costs by increasing the scale, by getting a bigger factory, getting a bigger restaurant, that sort of thing. You could usually reduce scale. So you could usually reduce like average cost by just getting bigger. Things that have decreasing returns to scale, these things are usually things like very, very small firms. So let's say you have a firm that's like stuck with a certain sized, say it's a restaurant and it's stuck with a certain sized kitchen. Even if you keep doubling all of the inputs, like you have twice as many chefs in there, twice as many cooking implements, you're still kind of limited. And even if you keep doubling those inputs, your average cost isn't going to be decreasing anymore. Where constant returns to scale usually describes like an overall economy, like a large economy where you have many, many firms brought together into one place. So next up, lastly, let's just do the cheat sheet. So the kind of basic rules you want to remember are these. Let me kind of like gray those out because they're not too important. So increasing returns to scale, if you increase the inputs by some same proportional amount, by that scaling factor z, we find production here is greater than just simply increasing that initial level of production by z. So you have increasing returns to scale. And single firms usually have increasing returns to scale. Decreasing returns to scale, that's where we increase the inputs by some scaling factor, by some proportional amount, and we find that our level of production is less than had we just increased that initial level of production. And that you get when you have a very small firm or some sort of situation where there's some sort of like other fixed thing that's restricting getting some returns to scale. So like, for example, a very small firm stuck with like a kitchen of some size, you can't just expect to double the amount of chefs and double the amount of inputs and continue to reduce costs. The next one is constant returns to scale. This is what we're going to see as an assumption, is an assumption in most of our models in intermediate macro, where if you double the inputs, you have equivalent of doubling that initial level of output. And those examples were examples of how you show that. And that's it. Oh yeah, the other thing I wanted to do was give you kind of a visual intuition for what's going on here. So let's imagine we have that Cobb-Douglas production function form. So that was this form here. So we have a Cobb-Douglas production function. What would that look like if we were to plug in different numbers for k and l? Let's just set a to 1 there. So what values of y would we get if for different values of k and l? And for that, we have this nice little chart here made by Wolfram Alpha. So we have a production function. And you can see the production functions here. So it's k to the 0.5, L to the 0.5, and it tells you how much output's going to be. So the height is production. This axis along here, which I guess is x-axis, is amount of labor, and then this axis over here is the amount of capital. So it tells you how, as you increase the amount of labor and the amount of capital, what you expect production to be. So I've set it here at constant returns to scale. So that, once again, it's k to the 1/2, L to the 1/2. The exponents sum to 1, so constant returns to scale. If I could just get it perfect there. So when you look straight across this way, so looking at labor of 5, this level of production right here is associated with capital at 5 as well. Well, I mean, as we go up along this line, remember the height is the amount of production. As we tick along this height, both capital and labor are being increased by the same proportion. So this point right here that I'm pointing to is about equivalent to capital of maybe 2 point something and labor of 2 point something. So when I get it kind of perfectly synced in that, that means every time we go up this way, we've increased capital and labor by the same amount, by some factor, scaling factor z, right? And you notice this is a straight line, so this is a constant increase in production. So right at this corner right here, this is for 5 labor, 5 capital, and we have about 5 production. If we double inputs, so let's increase capital and labor to 10, which is over here, we find that we get double the production. But let's say we go to increasing returns to scale. So with increasing returns to scale, so at this point right about here that I'm pointing at, we have capital of 5 and labor of 5, and you can see we have production of about, going straight over, maybe 75, 66, somewhere around there. So let's say we double the inputs. We double the inputs to 10 capital and 10 labor. We see that we more than double the output. We have 240 something. So where this point I'm pointing out is the level of production with 5 labor and 5 capital. You can see that here. So 5 labor, 5 capital comes to about this amount right here. Sorry. When you double the inputs from 5 capital and labor to 10 capital and labor, you get more than double the production. And let's go to decreasing returns to scale. So once again, this point, if I could get it just perfect, this point right here is the level of production with 5 labor and 5 capital. You have about 2.1 or so right there, 2.1 or so. If you were to double the inputs, capital and labor to 10, you get a much smaller proportional change in production. So now production's only like 2.4 or something like that. And you can see how that works with this. Okay, cool. Hopefully this was helpful. If you found it helpful, that would be great. Let me know if you have any questions. Oh yeah, if you found it helpful, if you wouldn't mind clicking the like button. Thanks and have a good day. Bye.